Again, in this video, I'll look at a couple of techniques for data compression. A lot of these techniques are based on the fact that if our objective again is to map a value k which is less than m equal to 2 power l dash to a value v which is less than s equal to 2 power l, where l dash is equal to n times l. Okay. Now suppose 2 power I less than or equal to k less than 2 power I plus 1. Okay. Now this can means now 2 power I plus 1 itself can be written as, I will choose some value say some radical or radix n, or sorry, not n, but let's say c. Okay. 2 power, this can be written as I power c plus some value. Okay. We can write I power 1 as I plus 1 power c whole power 1 by c. That is nothing but 2 power I power 1 I power I plus 1 power c times cth root of I plus 1 power c. This is nothing but 2 power cth root of I power c plus d, where d is equal to I plus 1 power c minus I power c. Right? This is, you can use binomial expansion, that one. But in general, it will just be I plus 1 power c. That means for a given value k, there will exist both I and a value d, such that 2 power cth root of I power c plus d will be this. So you just have to store I power c plus d to the power I power c plus d as your compressed code, or it could again be used, treated as a checksum only. Now the question arises, what is the value of c that we should take so that we are able to code a large information compactly? Is it just square sufficient, or do you have to take more than that? Okay. So we just try to quickly do it. So to determine c, right? So that means if we take two consecutive values of d here, we require I power c plus d plus 1 whole power 1 by c minus 2 power I power c plus 1 plus d whole power 1 by c. That is the difference. Okay. How much does a difference and increment of 1 in d code? What? How, right? Say let this value be equal to x. Fine. Now the binary log of x will give us the number of bits, right? By which a rough idea of the number of values of x will give us the number of values by which it is cut down. A single instance of coding of this, right? So that will help us to determine what the value of the c should be. Okay, so this you can write it as right 2 power I power c plus d plus 1 is equal to whole power 1 by c is equal to 2 power I power c plus d whole power 1 by c plus x. Okay. Now divide both sides by 2 power I power c plus d power 1 by c. You will have here 2 power I power c plus d plus 1 power 1 by c minus I power c plus d whole power 1 by c is equal to 1 plus x by 2 power I power c plus d whole power 1 by c. Okay. I'll just expand up to one term is sufficient here. You will get 2 power 1 by c times I power c plus d whole power c minus 1 by c is equal to 1 plus x by I power c plus d whole power 1 by c whole divided whole. Okay. So, right. So we can continue again like this. We will get 2 is equal to 1 plus x by I power c plus d whole power 1 by c whole power c times I power c plus d whole power c minus 1 by c. Okay. This is what you will get. This 2 can be written as 1 plus 1. You do just a binomial expansion again close to that. What you will find is that the length of L dash comes out to be, length of x will come out to be, I shall use this mod like operator to denote the number of bits for the value x, will come out to be L dash minus c minus 1 log L dash minus log c. So what I am assuming is, if we take each time the length of the information reduces by c log L dash, right? Right. If we are raising it to the power c, then we require c into c times log L dash must in itself be equal to L dash. Okay. That is c square times log of L dash must be equal to L dash. Okay. In other words, c must be equal to L dash by log L dash square root of L dash by log L dash. Okay. Right? If we are raising, if we are coding I power this thing, that means we require, for what the value of L should be, must be log of L dash into C must be equal to L, the length of the information. That is square root of log of L dash into L dash must be equal to L. Okay. Right? The value C is nothing but N, or the number, in other words, right? So we have to raise it to the power of this. Right? Sorry. So C square log L dash will be equal to L dash, and L itself will be equal to square root of log L dash into L dash. So that is the value of C, to which you should raise it and calculate square root of. So there will be a value. So the code will be I power C plus D will be the value that you will be storing there. So it should give you fairly close approximation, maybe 1 or 2 or very few iterations you can finish the coding of the entire thing. Okay. Another alternative is the same thing, only you can inverse the process as well. You can have 2 power I power 1 by C plus X whole power C, right? Right? Now that we require 2 power 1 by C 2 power I power 1 by c plus x whole power c is equal to 2 power I plus 1. We try to find x such that 2 power 1 by c plus x whole power c is equal to 2 power I plus 1. Right? Therefore, we have I plus 2 times I power 1 by c whole power c minus 1 plus c into c minus 1 by 2 I power 1 by c times, this will be x here plus times x square is equal to I plus 1, and I will cancel. You will get a quadratic equation in x, right? I power 1 by c whole power c minus 2 times so and so. Okay, so in other words, you will get 2c I power c minus 1 by c times x plus c into c minus 1 by times I power c minus 2 by c times x square is equal to 2. Okay, we can bring the 2 to this side and the equation can be solved for x. And then the code will be nothing but, you can store I here, right? And the value of x, you can have some kind of a simple bit representation, right? For x. This will be nothing but x by 2 plus x by 4 plus x by 2 power L minus n, or something like that you can try to do, or you can simply take higher orders polynomials and solve it and try to get a better value for x. So for a given value of k, you can try to code it either these way. These are two similar and related ways of trying to code it. So this way, and pretty much linearly can keep coming up with simple techniques also. Earlier in another video on solving a problem, I had given how you can code 2 power L dash as a value between 2 power L. If you have a k value key here, and a value v here. If s is equal to s power n is equal to m, and you have a value k here, you can take this as the value k power 1 by n is equal to b, right? Or v equal to k power 1 by n. Now what you can do here is, in general, if you find that whenever what you notice is when you take the power here, right, there are always more number of larger values and fewer number of smaller values. We know by probability, even if you just take a bit as a base, each time a bit decreases, the probability of a number which is decreases by 50%, right? So after a few bits, probability of getting numbers smaller than this length and all will be practically zero. After 2 or 3 means 2 bits means it is 3/4, and then after that, and so on. So after a few bits, it's very unlikely you will get values smaller than this if you're generating random numbers of this length, right? Now if you're going to take the key here as a value, you can use inversion as a technique here, right? What happens is larger values, more number of values of k will be mapped to the same value of v, more number of larger values of k will be mapped to the same value of v, and fewer number of smaller values of k will be mapped to that. But the probability of smaller values occurring for k is very, very less. Probability of larger values occurring. So this has a, whenever a particular function or an operation or a method exhibits a behavior that is the exact inverse or the opposite in this term, in this sense, you can try applying the inversion principle. That is, what you can do is you can code this as s minus m minus k whole power 1 minus n as the value v. Now what will happen is, because m minus k is small, right? So a larger value becomes smaller value and smaller value becomes larger value, and then you take a power. But then you want smaller hash value to become a larger value, so you do s minus that. So like this, if you do this in general, whenever the inversion principle can be applied, whenever the pattern of the data exhibits or follows a behavior or exhibits a pattern which runs the exact counter to or the opposite of what is favorable or desirable for coding. So you can apply this principle all the time, most of the time, right? And also pretty much you can keep coming up with any number of techniques like these. For coding information.